Yes, sir.
Good. The ice cream. Can you see this bulb screen, Putala?
Yes, sir.
Very good. So what do you feel? This one. So this generates, anyway, this emits energy, okay, in terms of light and heat both. A minute. Here you can see, if I take a big picture of this, yeah, right side, you can see this LED bulb. Two-pin bulb. Here, the big bulb here, you can see this filament here. When the electricity passes through this, okay, when the electricity passes through this, because of the resistance to the electric current or the electron flow, because of that, there is a glow. There is a glow because of the generation of heat. And the glow is the reason to emit light. The glow emits light as well as the glow emits heat. And you have to think of the energy balance here. So the electric power here. So that's why. So what kind of, so this is the system. This is the system, and the outside the bulb may be the boundary, and outside the, sorry, surface of the bulb is the boundary, and outside the bulb is the surrounding. So why this bulb is very thin? If this is thick, it's a resistance to the heat transfer. When there is a resistance to the heat transfer, the internal temperature build up. When the internal temperature build up, the lifetime of this filament may be short, or even this can get melted. So what is there really? So this is a closed system. Okay, no mass transfer, but only energy transfer there in terms of light and heat. Okay, so here, see, the light is another types of energy here. So what is the input? Input is electrical energy, but we call it a kind of work. Let's say example, work means, let's say, when you have a same filament in a, how to say, jug kettle, or when you boil the water using an electric heater. So what electric heater makes is, it is not heating up the water, but it is really makes the molecules move fast. That is what we call the rising of temperature. Moving the molecules means the heater is really doing a work on molecules. වතුර හීටරයක් අපි හීටරයක් වතුරකට දාලා වත් කරනවා කියන්නේ අපි හීටරේ තියෙන එනර්ජි එකෙන් molecules move very fast. Molecules are moving very fast because of the heat energy. So moving the molecules means it is something like there should be a force on the molecules to move. And the molecules moving means the force on the molecules, and the distance is there. Force and distance there means it's a work. That's why heater does a work on water. That's how the electricity works. Hmm. That's how the electricity works. So here when it comes to this system, here your issue is there is no mass here. Of course, there should be inert gas. There should be some inert gas, or even maybe vacuum is not possible. There may be inert gas, and then there is a filament here. Because of the electricity, this filament works on the gas. That is only very little part, and this moves. And anyway, that's how this filament heat transfer to the gas here, and then the gas transfer the heats to the surface, and surface emits the heat. And of course, lights also emit through the glass. Yeah. So that's how we can see this bulb is very thin. So what I want to say is, in the making of this bulb, that energy balance or the first law of thermodynamics applies. If someone has no sense of this first law of thermodynamics, it is very difficult to develop this. That may be the reason why the inventor of this bulb, Thomas Alva Edison, if as I heard, 999 trials to make this bulb, because those days no much of understanding of this energy balance maybe. So maybe he tried with maybe thicker bulbs, thinner bulbs, bigger filaments, and finally there should be a right match. There should be a right match to make it work in more reliable way to use it. You understand? Yeah. So you have to think what makes it several hundred times prior to make the bulb. So you will realize it is related to energy and matter interaction in this closed system. Yeah, that's why. Understand? Yeah. So when it comes to heater, immersion heater, immersion heaters, not immersion. So you'll see only the heater here. Not immersion. Even when you need to design design this one, this is not electrical, but this is mainly the mechanical water. Water is not there, but still you can see. You have to think of the application. So not just about the heater. So heater inside the water, how it works, how would be the energy balance, and based on that, you have to size the heater. If oversized, that's a problem. If undersized, that's a problem too. Yeah. So to get the optimal designs, you have to have this energy balance because that is a closed system. So the first law of thermodynamics is a very practical tool when it comes to applications. Even in the boilers, you will see the energy balance. When you see the burners in the applications, you will see the energy balance. Power plants, there also you will see the energy balance. You understand? You have to keep with that. Yeah. So I'm going back to the slides. Back to the slides. So that's why. So the energy balance is. So here the no mass, same like a bulb, same like a bulb. Only energy interactions in terms of course, electrical energy goes in and it turns into the. So that may be considered as a work instead of heat, because what supply electricity to the bulb, once go there only it works as heat, means the input is not a heat, then it should be a work. So logically in that case, so the input energy to the bulb system, if you take bulb as a closed system, the input electrical energy is something like a work. because that is not heat. But finally, that creates heat, work transfer to heat, and part of that is dissipate, part of that turns into the light, also dissipates, and there will be an energy balance. And also, there should be some level of rising of internal energy if there is some gas within the bulb. Okay? There is a gas within the bulb. Of course, should be inert gas. If oxygen is there, sure the filament will burn. Yeah? So, energy input in terms of heat or work, and because of that, there should be the change of the internal energy. Okay? So, this is a good slide. Let me make it big. So, the energy input net is the change of the system internal energy. So this energy input, because of the communicating of the system with the surrounding of this closed system, so this communication with the surrounding in terms of energy and work. E means energy and work. Okay. So see Q. So energy and work. Q. Yeah, Q is energy. W work is here. No mass transfer. So this is a closed system. Because of this W, let's say this is in, because of this heat in, there is a microscopic energy rise. Microscopic nature energy rise means the molecular motions change, the temperature change, and that related energy change, what we call the internal energy change. So we call this E net, but this is finally you will see this E net is the internal energy change delta U. Of course, no mass transfer. Yeah, so this is a closed system. Closed means something like, let's say, when the door is closed, no one can go in. So the system boundaries closed for mass means boundaries closed for mass means mass cannot pass through the boundary. Like gate closed, you cannot go in. Okay, so this system closed for the mass. Mass cannot go in. Can you sense the word closed? Closed means like close the door. When close the door, cannot go in. Okay, like that. Okay, good. So this is a closed system. Only the energy goes because of this energy interaction source. E means heat and work together. So there is a
Consider Sally one of the particularly
there is a internal energy change because of this E, the energy change, we call this internal energy change. So you have to think more and understand more about internal energy. But that is very important. And to me, this is the molecules, the motions. It's changing. The agitation, there is a change. The violence of the molecule, the level of the violence, it's change. And that is related to internal energy. Because these molecules are not silent, they are really violent. The fast movements, linear, rotational, and vibrational. Yeah. So this molecular violence or the motions, it's changed because of this E. If there is E addition, sure molecules will be energized more. That's the level of the energetic level of molecules because of this E in. If E reduce, the energetic level drops. When there is a release of energy from the system to the surrounding, the energetic level drops means the delta U is negative or the U drops. Yeah, that's what. So energetic level. So you can use E, U, and also the term simple E and simple U when it comes to the per kg or per unit mass. So this big U is for the system. So the small u means 1 kg of the matter in the system. So that's why the small u is intensive, but big U is extensive. You can understand the words intensive and extensive. Extensive means extent, yeah, whole size, whole volume, extent. Intensive means intense. That is really sharp and fine, and that is only for 1 kg mass or 1 meter cube volume. That is intense. Okay. So there is no flow here. Non-flow energy balance is this, because you have heat interaction, you have work interactions together. The energetic level of the system mass or matter in the system change from U1 to U2. So the change is U2 minus U1. We call it delta U. That is what delta Q and delta W together does. So delta Q and delta W together is, what is delta U? That is U2 minus U1. And this together you can say this is E, the energy input, or even using delta E is okay. So interchangeably you can use either E or delta E or delta U. But delta U is for sure here because of U2 minus U1. So delta means a difference. Okay, delta means a difference, but this is also can be considered as a change. So when you write the difference or a change, always change refers to the relative to the initial, the final. So U2 minus U1, final minus initial. So first stage and the second stage value minus the first stage value, that is the change. If the change is positive, we call this increase. If the change is negative, we call this decrease, dropping. So it depends on the sign finally when you calculate. Okay. And here delta t means initial time is t, delta t means the time increase or the time change or the time lapse for this process to happen, this delta E interaction. So during this time delta T, delta E energy interaction, so the internal energy change is same as delta E, that is U2 minus U1, the final state minus the initial state, the internal energy difference. I hope today you have a better understanding of this. So here you can see non-flow energy balance. So your heating applications, your boilers, here very little applications. Strokes, even this, whatever the strokes in the piston cylinder, you have to look into this. Yeah. So this is about some simple boiler designs. Yeah. Even pressure cooker design, rice cooker design, you have to depend on this energy balance. Okay. And I hope you can understand this and you can see this example in your notes. This is what we discussed last week as well. So here you can see compressed air in a cylinder. So you can see compressed air in a cylinder means this is a closed system. Otherwise you cannot keep the air compressed unless it is closed. That's the practical sense. At the beginning, this much internal energy, initial internal energy. At the beginning of the expansion, and an internal energy of 220 after expansion. So this is after expansion. So this is U2, 220. U1 is 440, and this is a closed system. So when your internal energy is changed from 220 to 440, okay. So this internal energy change means the net energy in. What is the net energy? The heat comes in plus the work comes into the system. Why here minus 120? The work. work, because here, if the work done by the air means this work is done by the compressed air. So compressed air does work, means the energy level of the air reduced. It does work on the surrounding, not received but delivered work. So as a receiving of work, this is minus. So heat in plus working is minus equals U2 minus U1. So this is the heat in, means this is a heat release. So very wonderful application. Yeah. This is a compressed air cylinder system application. That's right. So when you see this kind of examples, look into the practical aspects as well. Then you feel the value of the example. Yeah. It's a simple modeling of a compressed air in a cylinder. Yeah, it's a simple modeling. Yeah. And here you are using the energy balance or the first law of thermodynamics. This is the experimental based law. See how we are valuing this example. That's what we call learning. It is not about what is Q, what is W, what is U2, what is U1, and not only substituting and get an answer. In depth, there is some practical sense. That's how you should see and value the examples. Okay, Vitala? So that's why we have to learn everything. So you will see this in the notes as well. So let me. So till last week we came this. So here you can see 1 kilogram of iron and 1 kilogram of water. Temperature rise from 20 to 30. So this can be considered as a closed system. Okay. So you are just putting some energy in heating, but nothing goes out and no work out, nothing. So you energy in, energy in. So temperature rise from 20 to 30. 1 kg iron, 1 kilograms of iron, you need little energy compared to what the water needs to raise the same 10 degrees. Yeah, yeah, you have to understand why this is, because these are the metallic molecules and here the water molecules. You will see the difference here. So you have to inquire this, why is this? But you will see, if you need to store energy, you should not use iron, you should use water. But if you need to transfer energy, you can use iron instead of water. There are application interest as well. So when you see the data, you have to really see the application points. That's why. So this should be more than the data. You'll understand. That's why you need some effort, some interest, and a new way of learning, really. New way of learning. Give some real life to the learning. Right? So I'm helping you really, just pointing this kind of things. But 1 kg of iron is very small. See this size. It's dense. Right? Dense. But 1 kg of water is 1 liter. The 1000 ml. 1000 ml iron is quite huge, heavy. It's difficult to carry even. You can see the size-wise difference, the energy-wise difference. Very interesting, and this difference makes the material unique to itself for specific application. Very interesting. One more. Yes. Now we are comparing 1 kg iron, very small, 1 kg water, 1 kg air. What is 1 kg air? See here. Yeah, I will open it all. See, 1 kg iron per kg per 10 kelvins. To increase 10 kelvins, per kg you need 4.5 kilojoules. For 10 Kelvin rise, this means a 10 degree rise. Here, for water you need 4.18 kilojoules. See, compared to this, this is quite 10. And for air to rise 20 to 30, this is the continuation of the previous slide, 20 to 30. 10 degree rise, 1 kg air, you need 10 kilojoules, you need more energy. You imagine 1 kg air needs more energy to rise 10 degree from 20 to 30. It's more than the water, okay? And it's much more than the steel or iron. So you can see this. Yeah, these are the wonder of the nature, the wonderful nature of the matter. So you have to feel these things. That is very important. That's what we call the technology students. Yeah, the inquisitiveness, the interest to learn, to compare this, the contrast, to see and understand. This is very important. Otherwise, this is simple number memory, and you have no any differentiation of this, and you are not really learning. So you have to do this analysis. So I did this for you, and I got this from the information in your notes. Yeah. So we call, so finally this figure for 1 kg, this becomes 450 joules. For 1 kg, this becomes 4180 joules. For 1 kg, this becomes 10,000 joules. See? So this is 10,000 joules. And this is the table. So what we call, these are specific heat. So I want to explain you, I want you to feel what the specific heat means. Okay? Now learn this in your diplomas. Specific heat. You read the calculation. But you never feel the wonderness or the wonder nature of this with different materials, iron, water, air. You feel the difference of this matter. The same way, temperature you feel. So if 1 degree rise, how come the different values? Sometimes it is really unimaginable. Maybe if I ask you without showing this, you will see the lowest specific heat is from air maybe, but it is not, that's other way. So you should understand. Understanding this means you can apply. Okay? Yeah. So here you can see the specific heats. Yeah. I've got these tables, all experimental values. So steam, you can see the hydrogen 14,000. Okay. So here all calories, calories per joules. The time is running. Yeah, we have another 10 minutes. See, hydrogen is quite 14,000. So steam 2,000 should be at 100 here. So here steam 100 in this table. Joule per kg here. See joule per kg here. Joule per kg this column. You can see 2,000 here, 2009. Yeah. So the water for 4,000 something. Sea water it is little less. Hydrogen quite high. You see hydrogen. The energy need to rise 1 Kelvin is 14,000 joules. Is much more than water. Where is air? Air is 718. Okay, 718. You can see the C values, specific heat capacities. Interesting. So you have this. So actually you have to see this material are familiar to you. Okay. You may have the familiarity, at least you will feel this different. Maybe some gaseous form, some the solid form, some may be in liquid form. You have to look into this, but these are the mostly all in the solid forms here. So you can see the specific heat capacity values in 2 units, 3 units really. This is BTA units, this is on calories, this is on joules. Interesting, different units. So you can see all the units are used interchangeably, depends on the applications. So better note the units as well, but all are specific heat capacities, values of different substances. So you should know where to get these things. So here you can see some freon, the refrigerants. So some liquids here, some gases, some familiar materials should be there. Yeah. So this should be important. So when you do this application for the energy balances, because to see the internal energy change, if 1 degree rise, what is the internal energy change? Maybe it's a C value, we may not know. Yes. So here again, 1 kg, 1 kg, constant pressure and constant volume. So here maintain the same volume when you raise the temperature from 20 to 30. Here you maintain the pressure and you let the volume increase, and then temperature rise from 20 to 30 under same pressure. And this is your specific heat, 1.005 kilojoule. Here your specific heat is 0.718. You have to understand this magical nature. Okay? You have to understand this magical nature. Understanding this magical nature is what you call the knowledge, the wisdom of thermodynamics. Don't keep these limited to books and the formulas and to the words. Right? That is not thermodynamics. So you should really look into the thermodynamics. So see, yeah, very interesting this analysis. This really helps. So this tells that for gases, 2 types of heat capacities because of this wonderful nature. Constant pressure, rising of the temperature, the heat needed, constant volume, this one, rising of the temperature, the heat needed. We call this CV for constant volume, CP for constant. Yeah, Buddha.
Sir, we have another lecture 3:30.
Okay, then we will stop now. Okay. Yeah, what's the time now, Buddha?
50 now.
Eh?
3:50.
3:50. Okay. So let me stop the class now. So see you next week. Good luck then. Please go through this all, understand, and be mindful of the assignment, what I passed to you. Okay, thank you. Good luck. Yeah, I will stop the class. Goodbye to all.
Thank you, sir.
Okay, bye. Thank you.